My name's Alex Rodriguez, reminding you,
You don't need a contract.
you need a team of pros.
Hey, what's up, folks? Alex with Bay Cities Construction. We are talking about cantilevered columns. Obviously, we're talking about soft store retrofitting, but something you may not know. If you're considering a soft store retrofit and you don't know which methodology to use, or you're starting the process right now, you're going to totally love this episode, because today we're talking soft store retrofitting and cantilevered columns and what can happen as a consequence if you use the wrong methodology. So don't go anywhere. Stay tuned. Back. Alex Rodriguez here with Bay Cities Construction. Thanks for joining us on another episode of our construction show. It's actually episode 32. Can you believe it? So let's get into it. We're going to talk about cantilever columns. We're going to talk about special cantilever columns and ordinary cantilever columns. And the first rule of engineering is do not do harm. So as we talk about this, actually, before we get into this, let's talk about last week's episode. We talked about house bolting. So please, if you missed that, go back into our little YouTube channel and check out the library. We've got a lot of really cool information. And if you want more information on construction services or different construction projects, we have over 400 articles at baycitiesconstruction.com. All right, so let's get into the show. I'm trying to click here. Nothing's happening. There we go. All right. All right. Seismic retrofits for houses. That's episode 30, guys. You may want to watch that if you're considering retrofitting your place. It's not working. Oh, sorry, we're having a little technical difficulties. Don't go anywhere. I'm not saying. All right. So let's talk about tonight. We're going to talk about some of the codes. We're going to talk about this, what I think is an overly used phrase, value engineering, why it matters, and why it's important to get this right. You know, the city of LA basically building owners are undergoing renovations that are forced by this code of $1.2 billion. So the question is, are we getting it right? Are we using the money the right way? So that's one of the reasons that I created this little webinar today, is because of that. It does not flip over. Can you move that? It's really important to get this thing right. Yeah, you know what? Just give me that thing. Just give me the laptop over here, because no, it doesn't matter. Then I'll look at the thing. There we go. Oh, here. No, well, I can see that. That's good. Okay, sorry. Understanding the codes. Let's start with that, because that is the reason that people are doing this thing.
Maybe your mouse died.
There we go. No, that's it. Okay. So it's important for you to understand that the California code, building codes, all of the building codes in California, the structural, as they relate to the structure of any building, have to do with life safety. The building is never designed, unless it's a critical building like a hospital or a police station, stuff like that. But residential houses, commercial buildings, they're built to the life safety standard. Life safety standard is just that the building won't kill you. So it prevents collapse only. The building can still suffer major damage. It can result in a total loss. And that's just the current situation with the California building codes. So as people are starting to evolve, as really the push from CIOSC and other organizations, the push is to have a more resilient city, right? Or more resilient cities, right? So what we're talking about in resilient cities is in some cases the prevention of damage, and in other cases it's basically bouncing back after a major event. So not only will the buildings survive, but the buildings can survive a major event. And a good example of that are the building codes in Tokyo, Japan. Tokyo can suffer a pretty significant, scary earthquake, and they often do. and with very minimal damage. They can actually, they're designed to withstand like an 8, even an 8 plus. So that's something to keep in mind. So what's the difference between collapse and well, I guess these pictures illustrate a good example of what the difference is between life safety, and in fact, you could argue that in Mexico City, they don't even have a life safety standard, right? Because this building actually collapsed and it definitely trapped people in there. This is the 2017 Mexico earthquake, and on the right you see the Fukushima quake, a building that suffered pretty good amount of damage, but it did not collapse. So that's I think an important contrast to understand. And they're similar construction buildings, by the way. So tonight we're going to be talking about the cantilever column, and we want to get into this a little bit deeper so that you can have an understanding of how it's used, how it can be used correctly, and how it could be used incorrectly. So this is, by the way, a slide, the Siosk, this very, very talented engineer. I took actually a screenshot picture of this. I attended the Siosk event in Lake Tahoe this year. Really an amazing event. Very smart people there. Very dedicated engineers, and definitely a lot of experts in structural engineering there. So this is an example of a cantilever column, and a couple of things to understand of what's going on here is that the cantilevered columns, as they're being used now, they're replacing gravity members, okay? And that's not a good thing. When you replace one of the existing pipe columns on there with one of these systems, you're gonna have the beam do two jobs, or the column do two jobs. You're gonna have it hold up the gravity of the building, right? The gravity load of the building, and it's also gonna act as a lateral force resistor. So the current columns are only gravity members, right? That's why you may think like, man, they're kind of thin. You know, there's not a lot going on with them. And the new columns are so much thicker because the new columns, the I-beam columns in particular, are going to be made for lateral force also. So it's important to understand that. Okay, so let me back up. I want to talk to you about lateral force. Most buildings are designed to withstand a lateral force of about 2% of its height, right? So if a building is let's say 16 feet tall, it can withstand a lateral force that'll push the building 4 inches, maybe even 5 inches in any direction. But when the lateral force reaches 4%, excuse me, I'm not saying that right. When the lateral forces cause the building to sway 4% of its height, you're talking about 8-9 inches now, you start having a substantial amount of damage. And one of the goals of the cantilevered column or the moment frame or any of the other methodologies that we use, it's to prevent that drift from exceeding the 2%. Once you go over 4, you start getting damage, and the building starts to experience tremendous amount of damage at about 7% of its height. So if you're going from 4 inches to, let's say, 12 inches, the damage that the building will suffer is going to be pretty big. So let me show you this really cool graph. Why is that not clicking? There we go. So this is a really cool graph. Again, I got this from one of the presenters at the Siosk, and I took so many pictures and screenshots. I'm sorry I can't give the exact person credit, but there was a presentation given on the earthquake at Ridgecrest, and this diagram was created to compare the felt force of the shaking, and the dashed line is a representation of the existing codes. The dash and the solid line, it looks kind of like a plateau. In black, those are the current code, and then you can see in China Lake where the naval base is, you can see that the earthquake way surpassed the current building codes. And if you go over to the right, you could see that the lateral force, or the earthquake force, excuse me, did exceed the existing building code, but it was nowhere. It was not as severe as China Lake. Now, if you look at the heat map on the bottom there, those 2 points, you could see that China Lake was within the red zone of the fault rupture, and you could see that the rest of Ridgecrest was in the yellow to orange zone. And again, this is just a way to capture to compare the existing building codes. Want to compare the existing building codes with the actual felt force, because I gotta say that a lot of the kind of pushback that I get when I'm talking to building owners about this and preparing their building is like, we've had all of these earthquakes, and my building's been around since 1970, et cetera, et cetera. But if you look at this chart, you can clearly see that if we were to have a major event like that in the red zone, many buildings will suffer tremendous amount of damage. And it's actually proven. The China Lake facility, the naval base, they're talking about like $2 billion worth of damage to the naval base. So can you imagine if you have this kind of an event in a heavily populated residential area or commercial area? It's going to be pretty substantial. So I thought that this was an amazing graph created by one of the CIOSC members to show and give us a comparison, a perception of what we're facing here. All right, so let's talk about understanding steel and what happens. What happens to steel? So one of the other presenters, actually there were a few pretty impressive presenters. They're all pretty cool. There were a lot of different specialists. Some people specialized in wood. There was some specialists in steel. There were some specialists in forensic steel. A couple of guys who are basically experts in analyzing what happened during Northridge and some of the other earthquakes to steel members, moment frames and stuff like that. So in here, it's important to understand a couple things of what's happening here. So to the right, I don't know if you can. They see my. They can hardly see my. Here we go. So it's a profile shot. Here is the profile of the I-beam. Okay, that little dash mark represents the steel center of the I-beam, and then this is the new grade beam that it's embedded in. Okay, so all of these cantilever columns are set up like this. They're embedded in a grade beam. This green, these little green triangles represent the way that the I-beam is going to actually twist in place. And if you can tell from the picture below, it's actually experiencing a twisting movement. The engineers call that torsion and warping, really torsion. So that movement you could see in all of these cantilevered columns, the damage is going to be at the base. So what ends up happening is that once the damage has occurred and the building survives, assuming the building survives, this cantilever has got to be torched out. Building's got to be braced up if it's acting as a gravity member. You got to torch this out, and then you got to beat and remove the grade beam, the concrete grade beam that was installed on the ground. That's got to be completely removed, all right, under this scenario. To the left here, it shows an existing pipe column, which is your gravity, part of your gravity system of the existing building. And then the cantilever is connected to that section right in front of it. And they normally do that so that you don't lose parking, right? Like the posts, you got to line them up so that you don't lose any parking. So the idea here is that you install the steel plate, it goes and attaches to the drag line beam, and the cantilever, it's doing its own thing. Okay, the cantilever column is going to keep this. This is a profile of the beam. And by the way, if you're not getting this, please post in the comments below. I know it's a little bit difficult to explain this on a 3D, 2D. It's difficult to explain a 3D explanation on a 2D diagram. So the idea is that you have the cantilever in front of your gravity beam, and it's not a substitute, all right, which is better than if you replace it. However, this scenario has some issues because the way that this connection is done. This steel plate connected here, it could suffer torsion in itself, and it could potentially even damage the gravity beam. Potentially. So in this scenario, you've got actually a member column. This is actually a piece of a moment frame. So there's a column and a beam section here. And what they're talking about here is creating the damage. Instead of it being at the base of the cantilever, in this scenario, the damage would actually occur at the top, which is basically the definition of a special moment frame, right? That's the definition of special moment frame, is that the engineers are actually predicting where the yield is going to be. They're actually making it yield in a different spot. So anyway, that's what that is. So this is a test on a moment frame. So getting back to installing a cantilever, in this scenario, you're installing the cantilever column, or the new column, welded onto an existing gravity beam. And this kind of U form here, this is actually, I do know who put this forward. This was Daniel Cepeda's slide. He explained to us that it is very probable that the shaking from the shaking caused by the earthquake would cause this gravity member to experience torsion. Same thing for these floor joists that are on top. And in both directions, right? Because the earthquake moves this way, but it also moves this way, right? So the biggest problem with hooking up a cantilevered column to the existing gravity members is that you could damage the earthquake, because it's connected to the stiff lateral member, can actually damage the gravity members. Now this would not occur if you didn't connect it. This only occurs because of the way you connect the cantilever column to the gravity system. If you connect it wrong, you're actually going to cause a lot of damage. And you can ask any engineer, even the engineer that may be working on designing your project right now. If you ask them, are you using a cantilever column? Yes. The way that you're connecting the cantilever column, will it cause damage to the dragline beam? The answer will be yes. Most people don't understand that. Now, maybe you may ask, well, why would the city allow this? Why would the city allow the installation of a new element as the retrofit solution that's going to damage my building? Because the building department is only worried about life safety. Okay, life safety. This will not collapse. The building will not collapse. Okay, it will not. That meets the requirement. However, it is probably not the smartest thing to do based on what you're seeing here in this diagram. Does anybody have any questions about this? I'm really curious. If you have questions about this, please post them in the comments below. I'd love to address them. Here's another slide that the engineer put together. And in this scenario, there's a brace from the dragline member. So here's your existing gravity member, and here's your cantilever, and then you've got these weird braces happening here. So a couple different things happening. It potentially, you could cause twisting of and rolling of this member here, and there's definitely going to be some force pushing out. Not only that way, but on orthogonal on the backside. So these are things that are problematic. You want to take a break? Okay. So let's continue to talk about steel. As you can see with these examples, it's really important how this stuff is connected. You very well may get some plans approved by the city that will withstand the earthquake and it'll keep your building from collapsing, but they're definitely going to cause more damage to the building than if you would have used something else. Now, you may be thinking, why why did this thing even start, right? Like, why are we even talking about cantilevered columns? Cantilevered columns were approved to be used in sections of the building that you couldn't fit a moment frame. But many people, under the disguise of value engineering, right? We're going to value engineer this, meaning we're going to reduce the construction cost by putting in these cantilevered columns all over the place. In most cases, when you connect these cantilevered columns, you have a very, very high probability that the cantilevered column, after a major earthquake, will cause massive amount of damage to the gravity beam that it's attached to, whether it's steel or wood. You got to understand, this wood building, it was never designed to have such a firm, rigid element, such as a cantilever column attached to it. So you got to be very, very careful in how you do the attachment. And I'm going to show you, as part of this presentation a little bit later, how we did it, how we used the cantilever column, and why we did it that way. So let's move on here. The next slide is a pre-Northridge. For those of you that say, hey, you know what, I'm going to have somebody weld a moment frame, or I'm going to have somebody weld a column here. You have to understand that field welding is nowhere near as high quality as something that's done at the shop or that's done at a factory like, let's say, Simpson or Mytech, if you're talking about a prefabricated product, right? So Simpson Strong Time makes a moment frame, a special moment frame, and obviously Mytech, their competitor, also known by the trade names of Hardy, they make a moment frame also, a pre-manufactured moment frame. So here, there were these. This slide is from Mytech as part of that presentation, and they showed the fallout of an unproven weld in the field after Northridge. So the Mytech presentation was really very informative. They have, not only do they test these steel members, but they also have predictive technology on computer programs that can help predict how the steel will yield. It's really an amazing thing to see and understand how the I-beam members will yield. So let's talk about value engineering. That little term that we all hear. You're probably, if you're shopping for software retrofitting services, you're going to have somebody tell you something about they're going to say something about value engineering. Look, value engineering is not more for less. Value engineering is doing less for less money. So less money, less work, less cost. More work, more money. So it's important to understand that you're not getting a deal, you're just doing less, okay? And that's really the brass tacks truth of the whole thing. So cantilevered columns, the column itself, what you see in this picture, is cheaper than a moment frame, for sure. It does not perform anywhere near as good as a moment frame. Look at the top of that flange. You can see it's going to be about 18 inches. That's how it's connected to the building. Now, granted, they put a new beam there, it looks like, but that's its connection to the building. A moment frame, however, will spread the connection or the contact point over 17 feet, 22 feet, 30 feet, depending on how big the moment frame is, right? So you can't compare. I mean, think about it. You don't have to be an engineer to understand this, right? If you're connecting a building that weighs 250,000 pounds to 18 inches, what's better? That or connecting it to 22 feet with multiple connection points on the wood? By far, connecting it over 20 feet or 17 feet. It's a much, you're dispersing all of this energy into a larger footprint, right? And that's what you want. So, like this opening here, you could have easily put a moment frame there, but because they wanted to save money, they used that thing. So, not the best thing. One of my little quotes here: value engineering trend in software retrofit designs has produced plans that are inadequate and deficient. Now, they will get approved all day long by the municipality. There's no question about that. The question becomes in its performance. Look, you're going to spend a ton of money as it is. Spend the amount of money that's appropriate to give you a reasonable amount of protection for the building. You're fighting earthquakes, okay? We never say, you're going to hear somebody else say, you'll hear somebody else, so if you ever hear somebody say this software retrofit was over-engineered, you must assume that that person doesn't know anything about what they're talking about. Not even a little bit. If you understand that the earthquake that we're talking about here is going to produce a seismic wave that's going to lift the ground up 2.5, maybe 3 feet, and then bring it down, and it's going to occur over close to 2 minutes, okay? All you can do is hope that you did enough. There is no such thing as over-engineering for earthquakes. No such thing. It doesn't exist, okay? If you think about, one of the engineers explained this to me in a very clear way. If you've ever seen those movies where you see an atomic bomb detonated and you see the mushroom cloud and you see the wave of energy that comes through the ground first before the flow of the nuclear particles, of the kind of the fallout, the nuclear fallout, the ground actually moves in a wave. It gets lifted up a pretty good amount. So the wave requires that kind of energy. An earthquake wave will produce that kind of energy in the ground. The problem is that it isn't just one wave like in the nuclear testing that it's just done, right? When the wave passes, it's over. In this case, the wave keeps coming for over a minute, okay? That's a very big problem. That's a very big hurdle to overcome to keep the building from falling. So understand that there's no such thing as over-engineering. And if somebody tells you that, they don't know what they're talking about. Be 100% convinced, because that's the truth. All right, so why it matters. We're going to take a little quick break. We're going to come back, and we're going to continue our presentation. I hope you're enjoying it. Don't go anywhere. We'll be right back.
I love Los Angeles. Movie stars, surfing, one of the most diverse cities in America. Some days, it feels like paradise. But any second now, that could all change. Because the big one is coming.
We're better prepared for the big one than any big city in America, which is to say, we're woefully unprepared.
An earthquake so large that the Los Angeles you know will be gone.
It's going to be chaos.
Thousands of fires will break out all over the city. The power will go out. Clean water will be scarce.
They don't understand that it's not going to be just one big shake, but it's going to be thousands of shakes for months or years.
There's nothing we can do to stop it, but we can get ready.
Why it matters. I hope you guys liked that little intro. Brian found that it's part of the awareness campaign that the city of LA's put together, so we thought it was appropriate for this episode. So as we talk about why it matters, you have to understand that, like, it's going to suck if your tenants can't go back into the building and sleep there. Or if you live there, you've got to find somewhere else. For those of you that remember Northridge, there were people camped out at the parking lot at the hospital in Northridge because there was nowhere else to go. They didn't feel safe just staying out on the street. By the way, during Northridge, we didn't have 60,000 homeless people living on the streets in LA, by the way. So it's a very different dynamic of what we got going on now. So it's important. It's important for you to think about this in a meaningful way. I got another couple pictures here. This is part of Northridge earthquake. that the dragline, so this is called, for those of you who don't know what this is called the dragline beam. It's also the main gravity member of the opening, right? It's a big beam. And you can see that it rolled, and the bases broke off and basically allowed the building to collapse, or to oh, it's a partial collapse and not a total collapse, but it definitely it definitely became extremely damaged. So how do we get this right? How do we balance people's resources, money resources, with a solution that's going to work, that is going to perform, and it's not an easy thing, but it's an important thing to spend a lot of time thinking about. So in this building here, God, I cannot see. I know. There we go. Sorry, I don't know, technical difficulty of a mouse. All right, so this is our building on in North LA, adjacent to Beverly Hills. So as you can see here, we actually installed a cantilevered column, and we put in two new. These are called HSS columns. They're pipe columns, super thick, way stronger than what was there before. There's something very special about this building, however, that came into play. Not only would it be intrusive to put a moment frame here, it would be a little bit difficult, but one of the reasons that we were able to not have to install a moment frame was because this cantilever, this area here where the mesh is, this is actually ready for, in this picture it's ready for stucco. We've already stuccoed this building, but this section here is a true cantilever and was not originally designed with a gravity feed. So it didn't have columns like this, nor did it require it because of the way the building was framed. However, the engineers felt that during an earthquake, there would be substantial compression as the backside of the building moves up and down, and the seismic wave travels through the building. It would cause these sections of the building to compress and then to be in tension. So tension is pulling away, compression is pushing into the ground. So they decided that it was a good idea to install a cantilever here, but we were very, very deliberate in how we did it. And let me show you what we did. So if I could bring your attention to this beam here, you see this is an LVL beam. This is a manufactured beam, and it's a solid beam from one end of the building to the next. And then we put in these braces. Now, these braces are not connected to the actual dragline members, right? They're connected to gravity members, but they're connected to the floor joists. And the idea is that the brace keeps the building from shaking at the orthogonal, right, at the perpendicular. And obviously it's connected to this new beam that we installed. So this is going to protect you laterally, and then this is going to protect you laterally, but at the perpendicular, or the orthogonal. Okay. So what we have here is because we installed this new wood and this new wood, we created a predictable load path back to the cantilever. By the way, if and when this LVL section, the new beam, is damaged, the building will not collapse because it didn't need it for gravity. It did not need it for gravity. It's really here for lateral protection in both directions. If you notice, you could see the grade beams, right? They go this way, and then they also go at a 90 degree. Okay, so that is the key important thing. Now, for those of you that may be thinking, oh well, what about this pipe column here? That pipe column was holding zero weight. It was sitting on this funky little soffit setup, and it had no weight. In many sections, it wasn't even connected. Okay, it was a joke. So the owner felt like it needed it maybe 25 years ago, but it wasn't doing anything. So It wasn't engineered. It was a mess. So we completely ripped that out and started new. We created new load paths, and what you can see here is a very pretty. Let me give you a close up. Now, this here I'm particularly proud of. This section here, it's not completed. It doesn't have all the hardware yet in this picture. So this is a progress picture. So this right here, what you may be thinking it is a blocking, and it is a blocking, but it's not what you think. It's an actual 4x16 blocking. Now, that is a huge amount of wood, and it goes along the entire dragline opening. And we did that so that we can disperse. We're strengthening the entire area around the cantilevered column because we're assuming that we're connecting a cantilevered column to toothpicks, right? And that's a bad idea. So what you have to do is you have to reinforce the building by adding new wood, and that's what we did here. In addition to adding new wood, we put in this really cool angle connector that Simpson got approved with the city of LA. I think it's an HSLQ, and it's a heavy angle. It's basically a heavy angle. It could withstand a tremendous amount of lateral force. Now, instead of using little nails like you'll see in pretty much all the buildings up and down the block, this actually has 1/4 inch SDS screws, which is super strong. So why can we install this? Because it's a 4x, right? It has a lot of meat on the top, and obviously the beam is big, so you can, it has a lot of meat to screw into the beam. Now, I want to bring your attention back over to the picture because we did something to the existing dragline beam. This beam here is the gravity system beam, okay? And it is an actual I-beam. Most people think, oh, I have an I-beam, I have steel, I don't have a problem. Yes, you do have a problem. If this was a new building and you're using this steel, most likely you would have some type of bracing like this here. So what we did is we infilled the I-beam with lumber and through bolts, okay, to keep that beam from twisting. All right, it's going to keep this setup here will keep that building that gravity beam from experiencing torsion. Notice we have some LTP 5s above that. There's a nailer, and then the floor joists actually sit on there. So all of this stuff is connecting back into the cantilevered column, and it's going to have a predictable load path. I cannot stress enough how important it is to make sure that you have a predictable load path. Do not assume that the values that have been given for the different dimension lumber will perform. If you notice, I'm going to bring your attention back up here. The engineers, the city allows you to give the building a substantial amount of diaphragm resistance, lateral resistance for this little 1x6 subfloor. Those subfloors are crap. They're, for the most part, in really bad shape. So we've put in a connector, almost one on each one, to help increase the likelihood that it's going to connect and stay connected well. Because it is important to connect that subfloor to the floor joist. This is your floor joist. This is your subfloor. This is the little A35 clip that connects that to that. Now, you may be thinking, oh, what's that little clip going to do? Well, when you connect that little clip correctly, and you're connecting it to wood that's in better shape, you need redundancy, right? You need a lot of clips. You need it on each, almost on each one. But when you do that, as a whole, the system will work better. The best thing, obviously, would be to have plywood on the as a subfloor. That would be phenomenal, particularly 1 1/8" plywood or something like that. But none of them have that. They either have this diagonal crap or they have TNG 5/8, which is crap too, but it's less crappy than this diagonal stuff. So, okay. So this is the part where we talk about questions. Some of you folks may have, hopefully are a little bit more informed than you were before we did this little webinar. So I want to know what your thoughts are. What do you think? And if there's engineers watching, I want to know if you disagree or you agree with what I'm saying here. You know, I did have the opportunity to be with some very talented guys and gals, engineers at the CIOSC convention, and I took away a lot. The CIOSC convention, they weren't just talking about soft stories, but there were, like I said, there were seismic experts there. There were experts on wood framing, on diaphragm framing, and when collectively, when you understand, when you take sections, you know, the golden nuggets that each of them have to offer, you can really put together a full picture of what you're dealing with when you're trying to fight an earthquake. So really curious about what your thoughts are. Do we have any questions?
One of the questions, one of our viewers wants to know, how long does a soft story project actually take?
That's a loaded question, man. I would say you should probably be ready to do 4 months minimum. We looked at one today, which is going to be like 18 frames. It's going to be easily a year. So it depends on how complicated it is, the access that you have, but at the very least, you should count on about 4 months.
Another viewer wants to know, it looks like they already have plans.
Mm-hmm.
It says, what do I do now if my design uses a cantilever column?
Well, we would love to help you figure out a better solution. Some engineers are offering to redesign it. Very seldom, of the 100 plans that I've had sent over to me to be quoted, less than 2% had a cantilever column used correctly, or in a way that we would feel comfortable installing it. So the best thing to do is to redesign it, to have it redesigned either by the original engineer or by us, and use a moment frame if a moment frame is feasible, as far as if there's enough space for it.
Somebody else wants to know, I guess their property is located in an area that's not requiring the retrofit yet, so they haven't passed an ordinance. They want to know, should they do it if it's not required?
Yes, I think you should do it. I think if you have a house that was built before the 70s or before the 80s, you should probably have that bolted down too. We've got I've got some field pictures that I took today of how those houses are connected. As it is, the soft story buildings, if you fall in a red zone, they won't make it. Mathematically, those connections, the way that the floor system is connected to the dragline beam and the orthogonal walls, that connection will not withstand a red zone earthquake. For sure, guaranteed, won't make it. So if you consider this a preventive peace of mind insurance policy, that type of thing. So consider that as an important to-do list over the next few years. By the way, you can borrow money now at the lowest rate you historically could ever borrow money to do this, and the property values are up. So if you think about what's the best time to do this, it's now. You know, as far as the resources that you can tap into.
Another question, somebody wants to know, how can they make sure they're hiring the right person to do this job?
I think that it's very difficult for people to understand what they're getting for their money. The biggest problem that I've seen is that folks come into this thinking, I don't really believe that my house is going to fall. I really don't believe that the earthquake is going to damage my place. I just need to get compliant. That's not the problem you have. The problem you have is that the building is in an earthquake zone for sure, no doubt about it. There are faults everywhere around us, and who can do this for me with the most diligence? Who has enough of a sense of duty to get this thing done correctly? And somebody that I could trust to do this. I think that that's the paradigm of thinking that you should approach when you're trying to pick a contractor. If somebody's been in business for a year or 2 or 3 years, they're not qualified. Guaranteed. They're not qualified. They've never dealt with, and I'm not talking about you should have 15 years of experience doing soft stories. Very few people will have, because the soft story ordinance really got activated over the last 36 months, right? Or the last 3 years. So that's not what I'm talking about, but somebody that really has an understanding of stick frame, of wood frame construction, and somebody that has a good reputation over a long period of time. There's a lot of good contractors out there, and thank God, because there's definitely more buildings than what we can handle coming up that are going to be required to be retrofitted. But you want to look for somebody who's obsessed about getting it right. Okay. There's some of the larger companies, they've done a lot of them, and I've seen the plans and I've seen the work that they've done, and there's some very big issues with them. But that's not what this is. What this episode is about today. Today we're just trying to get you educated and have you understand that there is a right way and a wrong way to use cantilevered columns.
One of our viewers, I think they know that we went out to Ridgecrest. They'd like to know what your experience was in Ridgecrest after the earthquakes.
So so the rumor is that China Lake suffered about $2 billion worth of damage. When Brian and I were out there in the desert, aside from the houses and stuff that we visited, when you see the scarring, how the earth scars, and how the scarring is parallel to each other, and how separated it is, if you can picture in your mind's eye a track of houses along that section where the scarring occurred, it would be total devastation. I really, after visiting Ridgecrest, man, I really had a desire to get this right before Ridgecrest, but when I saw what an earthquake, what a real earthquake, a real strong earthquake can do, the understanding really came to fruition about we're hoping that we did enough, not over-engineered and all this other crap that people talk about all the time. When it happens, when San Andreas breaks, or when the Inglewood fault breaks, or the PV fault breaks, it's going to be a very violent, scary earthquake. The people that I talked to at Ridgecrest that were close to the red zone, there's a reason why you saw them sleep outside for 3 or 4 days. They didn't want to sleep in their house, and their house didn't collapse. But the shaking was not like anything that we experienced. I remember Northridge when I was a kid. I was in, and I even remember the '87 earthquake. And what is in those videos, like that video where you see the shopkeeper, the camera that was inside of the convenience store, that violent shaking where things are flying off the shelf, we've never experienced that. That was way stronger. Some people think it was like 37 times stronger than Northridge. So we've never experienced that, and we're going to experience that, I'm convinced, within our lifetime. So I think that it's really very prudent that we plan, that we do what we can to prevent fire damage to our houses. Bolt down your house if you haven't done so, if you're on a raised foundation, and have some precautions for your family. Have water, have some food. They're not going to come, okay? If we have these ruptures like we saw in the desert, in a metropolitan section, they're not going to come and help you. The fire department or the police department, they're not going to come. They're going to be so overtaxed, over inundated with real life-threatening emergencies that they're not going to come for your little fire. They're not going to come for some of this minor stuff. So I think that it's important, it's prudent that we prepare our communities and we talk to our neighbors, and have an understanding. Because if your neighbor doesn't put an earthquake shutoff valve, doesn't have a fire extinguisher, and doesn't do some of the preventive stuff, doesn't have food, it's going to be taxing on you, right? So it's kind of like a block by block preparation that you have to think about. So get out there and get involved. I've put fire extinguishers on my house. I got real large fire extinguishers. I've got food. We're putting in the gas shutoff valves next week, and I'm going to do with a bolt down. I've been so crazy busy with all these other jobs, I haven't had a chance to do my own house, but I'm going to bolt down my house within the next 4 weeks. So prepare. Do something. Do not be a victim. Do something proactive to prepare for this. This is going to happen in our lifetime, for sure. What else we got? All right. Hey guys, thanks for visiting. Thanks for watching another one of our episodes. If you're watching on the rebroadcast, please post your questions and your comments below, whether you like it or don't like it. I want to know. So if you're thinking about doing some kind of a retrofit, please go onto our blog page on our website, softwareretrofitpros.com/blog. There's hundreds of articles there to help you on BayCitiesConstruction.com. We've got dozens of articles on software retrofit. That's all for retrofitting and bolt down. So my name is Alex Rodriguez with Bay Cities Construction. We've been in business for 15 years. We can handle your architectural, your engineering, represent you with the city, manage your project, and look me up. Look me up if you're thinking about hiring a good contractor. Don't miss another episode. Get notified. Go ahead and click on the like button below. If you're on YouTube, make sure you smash that subscribe button, and you'll get an alert when we have a new episode. Thanks very much. If you want to call us direct, you want to be old-fashioned and just pick up the phone and call us, I'm here to answer the phone for you. We're here in beautiful Torrance, California, and we service all of LA. If you want to watch some of our feedback and stuff, please go check out our reviews. We've got a few of them. And I want to thank you again for watching our episode. My name is Alex with Bay Cities Construction, reminding you, you don't need a contractor, but you do need a team of pros.
Do you know that a big earthquake can produce a wave that's 2 feet tall? Hi folks, I'm Alex Rodriguez, and I want to protect your house for $199 a month. I'm the owner of Bay Cities Construction, and after visiting Ridgecrest, it's clear to me that you can prevent a tremendous amount of expensive damage by having a seismic retrofit done to your raised foundation. Have you ever wondered if your house needs to be bolted down? And have you ever wondered what could happen to your house if it's not braced and bolted down? Let's check this out. Let's get down and dirty. So this is how we do a bolt down. We bolt down the mud sill to the stem, then we connect the floor joist to the mud sill, and then ideally you connect the subfloor to the floor joist. That's the system to keep this connection intact while the floor is violently shaking. Our low-cost financing makes this project affordable. The process is easy. It only takes 1 day. We live in earthquake country. Dr. Lucy Jones reminds us that earthquakes are random. We can't predict earthquakes, but we can prepare. Remember, it only takes $199 a month to protect your most valued investment. Get peace of mind with a Bay Cities Construction seismic retrofit. Protect your largest investment. Go to BayCitiesConstruction.com and sign up today. My question to you is, can you over-engineer a house for an earthquake? Look at that. You tell me. The big question is, did we do enough? I'm Alex Rodriguez reminding you, you don't need a contractor. You need a team of pros.
So I hope you found this informative, but remember, you have to take action, okay? Now you understand what the risks are. Please take action. Do something. Your family's depending on you. My name's Alex Rodriguez of Bay Cities Construction, reminding you, you don't need a contractor, but you need a team of pros. Go to softwareretrofitpros.com and put in your information today. I'll go check out your place for free. My name's Alex Rodriguez reminding you, you don't need a contractor. You need a team of pros.